she'll be telling us about Bumpless, pipe dream, RSK, growth diagrams, and Schubert structure constants. So take it away, Daoji.
Thanks, Liam, very much for the introduction. And thanks for the opportunity to speak at this wonderful conference. I'll be telling you about Bumpless, pipe dream, RSK, growth diagrams, and Schubert structure constants. Just to get started, let me briefly introduce the wonderful combinatorial objects called Bumpless pipe dreams. So for some of you, this may be a review, but for others, this may be new. So let me just quickly define what they are. So the reason I like Bumpless pipe dreams is that it gives me a combinatorial formula for these very important class of polynomials in algebraic combinatorics called Schubert polynomials. So to define a Bumpless pipe dream, so I can think about drawing the Rotha diagram for the permutation. So here I have chosen this particular permutation 3, 1, 5, 2, 4. I construct the Rotha diagram, and I think about these strands as pipes, right? So in particular, if I write down the numbers 1 through n in the bottom, and then I follow these pipes, I'll be able to get the permutation. So I will be able to read off 3, 1, 5, 2, 4. And then, so this is a Rotha diagram. So I can get other Bumpless pipe dreams from this Rotha diagram by performing these moves called the droop move. So I'm not going to rigorously define them, but you can kind of see what they do. So these pipes literally droop and they move the boxes towards the northwest corner of the Rotha diagram. And then you perform all kinds of droops, and then you will be able to get all Bumpless pipe dreams associated to a particular permutation. And sometimes you see this definition of, okay, the Bumpless pipe dream is a tiling of an invariant grid by these 6 kinds of tiles. So these are basically the combinatorial objects I'm working with. And in particular, I'm also not allowing 2 pipes to cross twice, okay? So, and the reason, as I said, I like Bumpless pipe dreams is that they give me a combinatorial formula for Schubert polynomial. So let's see how that works. So if I want to get the Schubert polynomial for a particular permutation, I first write down all of their Bumpless pipe dreams, okay? And then for each Bumpless pipe dream, I'm going to assign a weight. So let's say maybe this Bumpless pipe dream, the weight is going to be a monomial. And how I get this monomial is going to be, I'm going to look at each blank box and then assign a variable indexed by the row index of that blank box. So in particular, this middle one is going to get me x1 squared, x2 squared. All right, and I sum up all the weights over all of these Bumpless pipe dreams, I'll get a polynomial in these variables, and that will be my Schubert polynomial for this particular permutation. So this is going to be my definition for Schubert polynomials today. And you might see other definitions, but this is the definition I'm going to work with in particular. So, okay, so why are Schubert polynomials important? So Schubert polynomial has very important geometric interpretation, which I'm not going to get into, but so combinatorially, they form a basis of the polynomial ring. And then because they form a basis, I can multiply 2 Schuberts and expand them back into this Schubert basis. And then these coefficients, these are called the Schubert structure constants. And in particular, for any permutations, pi, rho, and sigma, I know that these Schubert structure constants are non-negative. And this is by geometric reasons. So basically, geometrically, these numbers will mean that the number of certain triple intersections of Schubert varieties that you can obtain from pi, rho, and sigma. So for certain triple intersections, you can count the number of points. So these Schubert structure constants count the number of points. So that's why they're non-negative. But for me, okay, so we're doing combinatorics today. We'll just agree with the fact that the Schubert structure constants are non-negative integers. And there's this important special case that people have fully understood, which is when pi and rho are both permutations with a single descent at position k, and these are also called the Grassmannian permutations. So when this special condition is satisfied, the Schubert structure constants are called the Littlewood-Richardson coefficients. And there are many, many different kinds of combinatorial models for the Littlewood-Richardson coefficients. I'm going to review, well, not fully, but recall some of the basic facts about RSK later. But then in general, the Schubert structure constants, we still don't know what the combinatorial model is for these. And we've, as humanity, we have worked very hard for them in the past 30 years, but we still don't have a full combinatorial model for these Schubert structure constants. So today I'm going to tell you what they are in a very special case. Well, maybe not a very special case, in a more general case than the Littlewood-Richardson coefficient. So to tell you that in this case called the separate descent case, one model of these Schubert structure constants, but we'll get that later. So let me briefly review classical RSK. So thankfully, this is not the first time you have seen this notion in today's talks, but in any case, here it is again. So RSK is a bijection between the set of these words in this alphabet that consists of positive integers from 1 through k. This set in bijection of these pairs of tableaux. So in particular, P is a semi-standard Young tableau and Q is a standard Young tableau, and P and Q are of the same shape. And P is called the insertion tableau and Q is called the recording tableau. So because Q records every time where the box is added. And so this bijection is realized by this algorithm called Schoenstedt's insertion algorithm, which I will not go into details today. And there are, of course, many, many wonderful properties of the classical RSK correspondence. But today I will bring your attention to this particular one, which is there are two standard versions of RSK insertion, which is the row version and the column version. So the row version is sometimes also called the right insertion, and the column version is sometimes called the left insertion, because you can read your word from going in two directions, right? So if you go to the right, it's the right insertion. If you go to the left, it's the left insertion. So in the classical RSK, row and column insertions, they always commute. What does that mean? Let's say so this is about the insertion tableau. This is about the P tableau. So we start from any P tableau, and then we row insert a number, and we also want to column insert a different number. It doesn't matter what they are. And then it doesn't matter which order I perform these two operations. So the row insertion and column insertion always commute in classical RSK. So in the version of RSK that's more general in the Schubert context, I will give you a version of RSK, and then this wonderful identity will not be true, but let's get to that in a minute. So for today's talk, I would like to introduce this notion of bumpless pipe dream RSK. So this is an effort to extend what we know from the classical RSK to the full flag variety case with Schubert polynomials. And so this is an effort to lift what we know about classical Littlewood-Richardson coefficient and try to understand more about Schubert structure constants. Okay, so where does the bumpless pipe dream RSK come from? So here is my starting point. So I'm going to start from this very important basic identity for Schubert polynomials called Monk's rule. So what is Monk's rule? Monk's rule is this formula to multiply two Schuberts. So one of them is a general Schubert. So this is general, as pi is indexed by a general permutation pi. But then the other permutation I require to be a simple reflection. So when it's a simple reflection, I know that my Schubert polynomial is always of this form, is a linear homogeneous polynomial. That's a sum of x1 through the xk. And when my product is of this form, I know exactly how to expand this product into sum of Schubert polynomials. And in particular, I know the right-hand side. So the right-hand side is indexed by, so each Schubert is indexed by this permutation obtained by performing one more transposition of positions on pi, such that after you perform this transposition, your new permutation covers pi in Bruhat order in this particular way. So that your two positions you swap have to straddle this k in this way. So k has to be bigger than or equal to a and less than b. So this is a very specific thing determined by k. And because Schubert polynomials, they have combinatorial models. So I told you about Bumpless pipe dream, but more traditionally, there are pipe dreams. So you can also do this with pipe dreams. So I'm going to give a Bumpless pipe dream version. So you can think about this formula bijectively in terms of Bumpless pipe dream. So what do I mean by that? So on the left-hand side, we have a product of two things. So the first one, I can think about it as a single variable, xi. And then the second one, I think about it as on the level of monomial, I take a Bumpless pipe dream of pi. So my combinatorial objects on the left-hand side is this pair. And bijectively, this pair should map to some Bumpless pipe dream for permutation on the right-hand side. So on the right-hand side, we have a disjoint union of Bumpless pipe dreams for these permutations on the left-hand side of this pair. Okay, so in my work with Pasha Bilyavsky, we give two insertion algorithms that generalize, so two insertion algorithms that are bijective proofs of Monk's rule, but they're two different algorithms. And then one of which we call left insertion and the other we call right insertion. So why do we call these names? So if we're actually in the Grassmannian case, so where pi has a single descent at position k, and here we have this sk, then if you translate Bumpless pipe dreams to tableau, to semi-Young tableau, so there is actually a direct correspondence. So our algorithm actually agree with the column insertion and row insertion in that special case. This is why I call it a generalization. And then, so the right insertion algorithm is a extension of the bijective rule for Monk's rule that I gave a while ago, and the left insertion algorithm that happens in this work is new. So our paper is in preparation right now, and hopefully it will come on AlCoVE relatively soon. But in any case, there are these two different insertion algorithms that bijective prove Monk's rule with Bumpless pipe dreams. So you might be familiar with pipe dreams, which is a different kind of combinatorial model for Schubert polynomials. And you can ask, okay, what is the Monk's rule bijectively for Schubert polynomials? And this question has been answered. In different ways. So Billy Bergeron, in their original paper of RC graphs and Schubert polynomials, they gave a combinatorial proof of Monk's rule. And then later in the paper by Billy, Horvath, and Young, they gave a different bijective proof with pipe dreams. That's also, so there are also two different basically bijective proofs of Monk's rule. So now there is a canonical bijection between between pipe dreams and Bumpless pipe dreams. So we think that if you, under this bijection, these algorithms, they actually agree. So secretly what they did with pipe dreams a while ago, they were actually doing left insertion and right insertion, right? So we're just doing this kind of same story, but with Bumpless pipe dreams. But so we can kind of also see that in hindsight that their algorithms they gave with pipe dreams correspond to left insertion and right insertion. But in any case, remember that I wanted to talk about RSK. So let me tell you about how to extend this idea of bijective rule of Monk's rule to a version of RSK for Schubert's, okay? So remember that in RSK, you have a bijection between two sets. On the left-hand side, we had these words. So to generalize the words, I'm going to introduce a notion of byword. So that is going to be my new left-hand side. And on the right-hand side, I used to have a pair of tableau. So now I'm going to also replace that. So by the insertion tableau with a Bumpless pipe dream, and by replace a recording tableau by some chain Bruhat order. So let me just also be careful and define the kinds of objects that I'm going to use right now. So what are these bywords? Bywords, a byword now is going to be a word of biletters. So how do I define a biletter? A biletter is literally just a pair of positive integers, a and k, and I'm only going to insist that a is less than or equal to k, okay? And that is the only thing I'm going to insist on. So you might be familiar with notions like bounded compatible sequences or compatible sequences. This is not like that. So this is a much weaker condition. I'm not requiring any compatibility, just that the first letter is less than or equal to the second letter. And this essentially, this comes from Monk's rule. So K is going to tell me which Monk's rule I'm going to apply, and A is going to tell me that which variable between x1 and xk I'm going to use. So that's why A is smaller than or equal to K. So this is bywords. A biletter is just a word of biletters. And also to define my recording object, I want to define this K-Bruhat order, which is asking for more from Bruhat order. So we know that we have the notion of covering relation for Bruhat order. So a K-Bruhat order is asking for this W to differ from this V by this new transposition. And then in particular, so this is essentially, this comes from Monk's rule that you saw in the previous slide, right? So this K-Bruhat order is asking this extra condition in terms of K. Okay, so let me now talk about how to get my Bumpless pipe dream RSK. So because Monk's rule tells me two different insertion algorithms, so I can pick one. So let's say I pick the right insertion algorithm. So given any byword, I want to iteratively insert each biletter to the identity Bumpless pipe dream. So every time I'm performing an insertion algorithm based on right insertion or left insertion that I got from the bijective proof of Monk's rule. And so therefore my insertion object is now a Bumpless pipe dream, and my recording object is going to be this chain in K-Bruhat order, because every time I perform an insertion, my Bumpless pipe dream is going to change from one permutation, is going to change, and then the permutations are going to be different. So my recording chain essentially records how the permutations change. And then the decoration on each edge is going to be specifying which Monk's rule I have performed. So this here 3 corresponds to this 3, this 2 corresponds to this 2, and this 2 corresponds to this 2. Okay, so and in particular, in the classical RSK, so how do I recover classical RSK from this picture? Well, if I take the K to all the subscripts to be a single K, that will recover my classical RSK. So if I decorate a word with the same K, so I will change a word to a byword. So in that case, I can recover the classical RSK. And I told you that there are 2 different insertion algorithms. So you can do this with left insertion, or you can do this with right insertion, right? So here there are 2 different versions of RSK, and you can see that this is very different from the classical RSK, because in general, this left insertion and the right insertion, they highly do not commute, right? So therefore, there are a lot of nice properties about classical RSK do not directly carry over with this more general version of Bumpless pipe dream RSK. And in a sense, this is kind of, we can see this as a way to appreciate the difficulty of the problem why Schubert calculus is difficult. This is kind of a lens through which you can see is because right insertion doesn't necessarily doesn't always commute with right insertion, but we are going to be able to say in a special case when a right insertion and left insertion would commute. And in that case, we'll be able to say something very productive about Schubert structure constants. Okay, so that is my brief introduction about the Bumpless pipe dream RSK. And as promised, I will give you a rule for Schubert structure constant in the what we call a separate descent case. So in order to do that, I will need to switch gear and talk about some completely different object. This is called Lenard's growth diagram of permutations. So this is different than Bumpless pipe dream RSK stuff. So if you have gotten lost, this is a good place to come back, probably. So Lenard defined these growth diagram of permutations as an effort to generalize Fomin's growth diagram of partitions. So Fomin's growth diagram of partitions is this 2D picture, essentially, that helps us really to understand the famous Judetecan algorithm, right? So Lenard generalized this to permutations in hope to say something about combinatorial rule for Schubert structure constants. So let me tell you briefly how this is defined. So a growth diagram is a matrix of permutations. So I have these pi with double indices. So this is a matrix of permutations. And each row and each column is a chain in the K-Bruhat order I just defined. And then I'm also requiring a global condition, which is that for every column of horizontal edge, I'm requiring each edge to be decorated by the same K, meaning that it's going up by the same K in the K-Bruhat order. And also in each row, I'm decorating it with an L. Well, so in each row of vertical edges, I'm decorating it with the same L. So, okay, so this is not the end of it. So, so there's also a really important local condition that really defines what these growth diagrams are. So let me tell you about that. So let's say if I want to construct a growth diagram, how would I do this? Okay, so I would start with a chain in K-Bruhat order from the identity permutation. I go up, so each step I go up by, in the K-Bruhat order by some K, doesn't matter what they are, they can be different, to some permutation that's over here in the lower right corner. And then from the lower right corner, so okay, so here identity, so within K-Bruhat order, I'm going up towards the direction to the right. And when I'm go up, I go from this permutation to this other permutation. I also go up a chain of permutations, and I also require every step I go up in K-Bruhat order. So let's say I fix these two chains, and I want to fill in this growth diagram by this growth rule. Okay, so what does this growth rule say? The growth rule say that, let's say I know these three corners of a local square. I have decided what pi rho sigma are, and I've decided that they're related by these K covering relations. So if I ignore these covering relations, I know that there exists a unique permutation that uniquely completes this Bruhat diamond. So this is just how Bruhat order works, right? So if it so happens to be the case that this sigma, which completes the Bruhat diamond, also satisfies these conditions given by these K covering relations on these edges, I put the sigma there, okay? So otherwise I don't put it there. So I just copy row over, I just do this. So what does this mean? This means that once I uniquely fix these two chains, I'll be able to uniquely fill in this growth diagram completely, and I will get my matrix of permutations, right? So here's an example showing that depending on what these Ks and Ls are, so I could start with the same pi rho and sigma, get to different results because I'm putting different conditions with these decorations of the edges. Okay, So that's the growth diagram. So why did Lennard introduce these growth diagrams? Well, because we want to solve Schubert calculus, right? So Lennard 17 gave a rule for multiplying two Schubert polynomials in the following case. So what did Lennard come up with a rule for? So I'm asking V, one of the permutations, to be a Grassmannian permutation with a single descent at position K. Okay, and I'm also asking W to satisfy another descent condition with respect to K. So W has all descents greater or equal to K or smaller than or equal to K. Under this condition, Lennard was able to give a rule for multiplying these Schuberts. Well, Lennard was not the first person that gave such a rule. So the first person that gave such a rule was Kogan. So Kogan gave such a rule in probably the year 2000. And then there are also a few different rules that came after Kogan's rule that solves the same problem. So we took Lennard's growth diagram and generalized this to a more general case where we relax the condition on V. So Lennard also only allowed V to have a single descent at position K, but here we're asking as long as V have descents less than or equal to K and W has descent greater than or equal to K. So this is the case called the separated descent. So this condition is first introduced by Knudsen and Zingestan in their work with puzzles. So they have a very high-powered puzzles rule that also could do this. And as far as I understand, this hasn't been written up. But then later, I gave a separate rule based on also Bumpless pipe dream from a different angle that solved the separate descent case. The reason that we keep working on this is that we want to try different techniques and see how far they could get us, and to kind of attack this problem from different angles to see where we run into walls. Okay, so let me also briefly say that why does growth diagram help us compute Schubert structure constant? So what is the growth diagram counting? Okay, so the basic idea is that, let's say we want to multiply SV times SW. So these are the product of two Schuberts we care about. I would really like to choose two special chains, one for V and one for W, such that the Schubert structure constant, this number, is equal to the number of chains that go up from this W to U that rectifies by the growth diagram. Rectification means filling this diagram. So after this rectification, I'll be able to get this chain on the left-hand side. I would like this chain to agree with whatever special chain I picked for V, right? So this is kind of the basic idea how I can express these Schubert structure constants with these growth diagrams. And where is the difficulty? So in the Grassmannian case, when V and W are permutations of same descent with a single descent at position K, it doesn't matter what these chains you pick. You can pick any chains and this would always work, right? But in the Schubert case, this is just highly not true. So Lennard was able to say some things. I would like to remark that the technique that we use, even though we both use growth diagrams, the actual technique of proving the rule is very different. So our rule is based on insertion, and in particular, our rule is going to be a bijective rule on the level of monomials for Schuberts. But Lennard studied some relations on these words of transpositions and how they interact with this growth diagram. So I don't think his rule is bijective, but our rule is bijective on the level of monomials for Schubert polynomials. So how much time do I have? I have like 1 minute.
About a minute would be good.
Okay, yeah. So basically, let's tie these together. Well, in 1 minute, let's tie these together. So we can incorporate insertion and RSK. Insertion and growth diagram in the following way. So as I said, insertion in general, they very much don't commute. But when when they satisfy, the two biletters are indexed by these K and L, satisfy a given condition based on descent. So pi has, we look at the first descent, the last descent of pi. And when they satisfy this descent condition, I can say that these two, left insertion and right insertion, they commute. And in the case that they commute, I can use this growth diagram to choose these special chains when W and V have separate descent that kind of propagate this commutativity over globally by this growth diagram, such that whenever you go a step to the right, you do a right, in the growth diagram, you do a left insertion. Whenever you go up, you do a right insertion. In this particular case, it wouldn't matter which path you take. And then so this is a particular special case where I can use growth diagram and insertion to say something about Schubert structure constant. So in this case, in the case of separate descent, Schubert structure constant is accounted by the number of growth diagram given of the form. Well, for this particular V and U, I can choose special chains such that, you know, growth diagram is counts the number of Schubert structure, well, counts is CUVW, that is Schubert structure constants. I will end my talk here.